My name's Matt Pearce. I'm from Mott MacDonald, and I'm going to give a brief overview really of our use of IDEA StatiCa at Mott MacDonald. So here's what I'll cover. Firstly, a quick introduction to myself and Mott MacDonald. I'll then give an overview or potted history of how we've approached connection designs in the past and how we've brought Statica into that process. So, as I said, we'll cover Wembley Stadium, which is going back 15 years or so, moving on to Wynn Palace, which is a casino in Macau, to Jakarta Velodrome, Waterloo Station this year, and end with a conclusion. So just quickly about myself, I'm principal engineer at Mott's. I started with Mott's in 2007. I started out in their Croydon office, and after getting chartered, I felt like a break from Croydon, so I moved to Hong Kong, as you do. This is to work on the Wynn Casino Palace in Macau, where I was based on site for a year. And I was also based in a steel factory in China for my sins. Also worked in Singapore and then returned to the UK in 2015. And now sort of taking on a role as digital design leader for the building structures practice, so looking at exactly this sort of thing, which is standardizing processes, software, and also looking at automation and generative design. So hopefully you've heard about Mott MacDonald. They're big. We're a global engineering management and development consultancy. We're one of the largest employee-owned firms in the UK, 16,000 employees worldwide, 180 offices, 50 countries, 6 sectors, and that's that. So casting back to 15 years ago, so as I said, I'd like to give an overview of the approach that we've taken to connection designs over the year, more recently with the use of Statica. So heading back to 2003 in the Wembley Stadium. So Mott MacDonald were a consortium team with Connell Wagner and SKM to provide engineering design. The stadium is designed to hold 90,000 people and features high level of hospitality fit out, and it also can host soccer, rugby and athletics, although it rarely does. The stadium roof is supported by an iconic 135-metre arch and is visible across London. And what's unusual about the roof is that the arch supports about 70% of the roof through a series of cables. So although we weren't employed to do the connection designs, we were, because some of the connections were so large. For example, the arch base for the roof, it carried about 70% of the roof load, and so corresponding the forces are absolutely massive. So it says there 17,500 kilonewtons horizontally. So this drum is basically the shear key that gets embedded into a huge lump of concrete. So due to the complexity of the base connections, we were doing 3D elastoplastic analysis using ANSYS, which was sort of the go-to at that stage. However, as you can imagine, it took a massive amount of time to model the elements, and it was not an efficient process, but it was necessary at the time. So moving forward to 2013, so this project I worked on, this huge casino complex in Macau with a cost of approximately $4 billion US. We designed the podium structure for the casino. The podium stretched about 800 metres end to end, with a total floor area of approximately 300,000 square metres. The structure comprised about 25,000 tonnes of composite steelwork, about 10,000 steel elements, 11,000 connections, 800 connection types. So as you can imagine, for a project of this size, process was everything. So we were using bidirectional links between Fast Track, as it was then, TSD as it is now, and Revit to design the steelwork. So the Fast Track models were pumped straight to Tekla structural design, Tekla structures for the fabrication modelling. That was the good part. The bad part was the connection designs were all done manually with a 2D process. So they were basically 2D drawings of the types, and then these were manually put into the Tekla model. So although the process is relatively streamlined, it still required like a significant amount of effort to produce bespoke spreadsheets to design the non-standard connections. We used Robot for some of the simpler thin plate connections, but even that required additional spreadsheets to do the checks that Robot wasn't doing. And there were also some areas where designing the connections in 2D led to coordination issues, to put it mildly, at some of the more complex nodes, leading to local design modifications. So moving on again, so this is only 3 years later, but we had another project with a large steelwork component, which was the Jakarta International Velodrome. It was built for the 2018 Asian Games in Indonesia, which just took place in August, so only a couple of months ago. We were working for the design and build contractor ES Global, who specialise in fast-track and temporary venues. The key features of the venue include seating for 2,000 spectators, a UCI standard cycling track, and a lightweight steel roof with a membrane fabric covering. So the main challenges are listed here slowly. So it was a long span structure. So as you can imagine, there are large forces, although it was a two-way portal frame effectively. So the loads were distributed, but they're still substantial. It's in a seismically active region in Indonesia, as we've seen just this week. And together with the high occupancy in the building of 2,000 people, this put it in a high-risk category building. A lot of the steel was architecturally exposed. One of the unique features of the steelwork was that it was comprised of approximately 75% reused modular components, which had its own bespoke connections that allowed it to be built very quickly. But that led to some complexities. And then it is also designed to American codes with local Indonesian parameters. It was modular design, so that it was fabricated in the UK and then shipped all the way to Indonesia. So that meant that we had to fit everything within shipping containers. They were the largest shipping container we could get, but they were still only 12 meters long by 3 meters wide, 3 meters high by 2 meters across. It was a very tight design program of only about 9 months, and a very tight construction program of only about 18 months. So before commencing the detailed design, we carried out an appraisal of the available software for the connection design. We were prioritising software over Excel spreadsheets, as this made checking easier. In addition, although we had many design spreadsheets for Euro codes, we didn't have as many for the American codes, particularly for the more complex connections. So what we did was categorise the connections into 4 main types, as you can see here: base plates, end plates, welded tube connections, and fin plates. Robot, which we had used on the Wynn Casino project, fell at the first hurdle because it couldn't design for American code, so that was out. We looked at Bentley, Limcon, and RISA, but they had AISE checks for the simpler connections, but not so much for the complex welded tube connections. And then we've seen that IDEA StatiCa is beginning to be used on some high-profile projects, and seemed to have the capability, so we decided to trial that. So this is an overview of the connection design process. So we started out with a sort of integrated structural and architectural parametric model in Grasshopper and Rhino. This allowed us to generate the wireframe model for the Rhino, a wireframe Rhino model that could be exported to Robot. All the connections were designed in IDEA StatiCa, so we were still manually exporting the connection forces to Excel and then into StatiCa. We were on version 7 at this stage. The connections were then sketched and sent to the fabricator. The wireframe geometry from the Rhino model was taken to AutoCAD. I know AutoCAD's not exactly high tech, but it was what the fabricator wanted to use because it was 75% reused components. They had AutoCAD blocks of pretty much all the connections that they wanted to use and all the components that they wanted to use. So we couldn't force their hand on that. So we exported the Rhino model wireframe directly to them. Then they implanted all their standard blocks. There were some bespoke components, so that the arches that these primary arches that span sort of over the main area was bespoke, made out of CHS sections. So the connection details are modelled in AutoCAD. It was fabricated in the UK, and the steel was erected in Indonesia. So the main outcomes of using StatiCa, I would say, that the steelwork connections were designed in only about 2 months, which was actually a saving of about 2 months on the original design program, just because of the length of time for shipping and import duty and all the rest of it. When the steel arrived in Indonesia, we had to get the steel out even earlier than we originally planned. But because we were using this new software, it did make it just about possible. It did go in a few later deliveries, but it's saved a lot of money in the connection design. The time is money, basically. Because it's the first time we were using it, we were doing hand checks, and it did show pretty good correlation with these hand checks. It still did require some manual manipulation of the output so that they were turned into sketches for the contractor. And this is just an image of the event in August. So moving on again, some people in the room might recognise this. So this is this year, Waterloo Station, where there's a huge upgrade scheme called the Wessex Capacity Upgrade. This involves a number of enhancements on the Wessex line. At Waterloo, this includes lengthening of platforms 1 to 8 to allow 10 carriage trains, reopening of platforms 20 to 24, which are located in the old Waterloo International Terminal, a new concourse connecting the ticket hall to platforms 20 to 24, and a new steel frame roof covering the new concourse. So Mott's were the designer for the steel frame of the info room, and Born Steel were the main steel contractor carrying out the works. As the connections and the frames had such a high degree of interaction in terms of structural behaviour, it was decided that some of the Mott's team would be seconded to Born Steel to facilitate the coordination of the connection design and the primary steelwork design. So that blurring of structural engineer and fabricator became very blurred indeed. So the key challenges for the project are listed here. So it was fully glazed, so it meant that it had very tight deflection limits, which meant that the connection stiffness had a huge role in terms of the overall stiffness of the structure. We had significant bomb blasts, sadly, because it's a railway station. It's architecturally exposed again, construction over a live railway station. It's built on basically whatever you can find underneath Waterloo Station. So it had quite complex substructure interaction with the steelwork, which led to basically putting columns wherever we could find something that was strong enough to put it on. So there's complex load pass through the steelwork as well. There's limited site access, and again a tight program. So just focusing on example of the complexity in the connection design is one of the connections for the west facade. So the connection comprises a vertical wind truss formed from an RHS outer cord, which is the vertical element, and a CHS inner cord and lacing elements. Attached to this were 2 RHS transoms and 4 McAloy tension bars. So this shows the sort of the performance requirements for the connection, just this one connection on it. So it was architecturally exposed. It had a 120-year design life. We had to use tension-only elements for the macalloy bars. Because it was architecturally exposed, they wanted the bolts to be concealed, so only the pins of the macalloys were exposed. The RHS transoms were fixed in the major axis, pinned in the minor axis, and axially stiff. Don't ask me why, I didn't do the original design, but it meant that the stiffness requirements were particularly complex. We had 3 different sets of load combinations, ULS, accidental blast load, and then post-blast load, and non-slip connections at service for the transoms. And because the sections were highly utilised to make them as small as possible, they had high internal forces, which meant we had to model the forces going through all the elements. So the first challenge was to apply load cases to the connection due to the number of combinations totaling more than about 3,000 combinations. So we enveloped the forces into 3 main types, ULS, blast and post-blast. Although this reduced the number, we had to include the forces in the RHS, which meant that the forces had to be in equilibrium. Because they were envelope forces, they weren't in equilibrium, so we had to then look at increasing the forces in some elements to achieve that equilibrium in the connection. The next challenge was on the stiffness requirements for the transom. So as the connection is required to be axially stiff and fixed in the major axis while pinned in the minor axis, we looked at a range of options, balancing the design requirements with buildability and the fabrication time. So using IDEA StatiCa, we were able to assess the stiffness of these options to come up with a balanced connection solution. This did, however, lead to the connection having some minor axis rotational stiffness. So we tackled this by using the rotations from the global model analysis results to assess from the moment rotation graphs what the predicted moment would be in the connection. And then the connection was then checked for that moment. So it's safe to say you wouldn't do that by hand. So finally, the connection calculations were output and marked up to allow the steel fabricator to input into the Tekla structural model. I would say that this is one area it doesn't seem to have changed from before. We've seen earlier that there's steps to make this a more streamlined process. So the main outcomes of the project, it provided comprehensive calculation reports that were approved by the design team, not just because they were Mott MacDonald. The stiffness properties could be fed back to the design team and incorporated into the frame design. So there's that real interaction between how the connections perform with the global analysis model. It did require a lot of work to envelope the connection forces, and it did require a lot of manipulation to provide the sketches to the contractor. I'd say in an ideal world, the connection forces would all be output from the analysis model, in this case robot, designed and then pushed automatically into a fabrication model, for example, Tekla structures. I think there does need to be some steps in between before we go there. So I think firstly on the loads, the Eurocodes have made the number of combinations required so large that running IDEA StatiCa for every combination would have taken days. So I think it would be preferable if we could somehow envelope the connection capacity somehow and then plot the load combinations against that sort of envelope. I think secondly, grouping of connections is required both in the analysis software and Tekla, so that a single connection type in IDEA StatiCa can extract loads from multiple connection nodes in the fabrication model. And I think in the intermediate stage that it would be great if there was a way of outputting those sort of engineering sketches automatically. Overall though, the IDEA StatiCa did allow us to design a much wider range of connections in much less time, and we were able to look at the stiffness behaviour of connections to see how this interacts with the global structural analysis. So just as a summary of what I've been saying, so it can design a much wider variety of connections than other software currently on the market. It can save time on designs, particularly complex designs. It can carry out the stiffness checks to verify the global modelling assumptions. It definitely would work best with a fully integrated analysis and fabrication workflow, and could benefit from sketch outputs in the meantime. So that's it really. So any questions? Well, thanks for listening.